My honor and privilege to start this last session of this excellent launch event. It's an important session. It's really, we have two excellent speakers in this last session that really represent the heart of what the CMIH stands for. There are two exciting talks by two cherished Cambridge professors. First talk will be by Mihaela van der Schaar, who has a very impressive track record, both with industrial experience, academic experience. Started off in the Netherlands, California, more recently moved to the UK in Oxford, Alan Turing Institute, and now finally we have you here in Cambridge. Highly influential, covers a breadth of topics, and I'm really keen to hear your talk, Mihaela. The floor is yours.
Thank you very much. I'm going to minimize all of you. So thank you very much, Carola, John, and James, for inviting me to give a talk today. I really feel that there is a lot of overlap and exciting activities at the border of my research and your center. So this is why I decided to talk today about a few topics where I feel a lot of interesting research is yet to come. I'm going to describe briefly the problem and what we have done so far. But again, I feel that in all these three topics, it is only the beginning of the journey. And more generally, I'd like to talk about why I feel that medicine and more generally healthcare are such exciting new frontiers for machine learning. I'd like to thank my research team, my PhD students and postdocs that contributed, of course, enormously towards this agenda. Our group's mission is to move machine learning from art towards science by developing machine learning methods aimed at empowering rather than replacing clinicians. We hope that these methods are going to empower clinicians and medical researchers to deliver bespoke medicine, understand the basis and trajectories of health and disease, empower healthcare professionals and patients, inform and improve clinical practice, as well as enable us to better utilize available resources and reduce cost, transform population health, excuse me, health and public policy, and enable new discoveries. Our group research can be really divided in a few key pillars. One important challenge for research, for researchers like me in machine learning for medicine is the availability of data sets. It is very difficult to get data that is of high quality that we can then use to build our analytics. Hence, an important pillar of our research is generating synthetic data, our machine learning methods to better generate and evaluate synthetic data. And the reason this is challenging is we want to generate data and create generative models that have high fidelity, but also privacy guarantees, potentially differential privacy or other type of privacy guarantees. So quite a lot of research happens in our lab over the last 5 years, generating synthetic data such that we can then share with machine learning researchers this high quality data without the fear of revealing anything private about the patients. And then train machine learning models and compare machine learning models on top of the synthetic data, and then take this synthetic, these models that were trained on the synthetic data to the real world, to the real data, and ensure that indeed, even though they were trained on synthetic data, they are going to work well in practice on the real data. Another part of our research focused on developing analytics to empower clinicians and medical researchers. Individualized treatment effects, time series data analysis, feature selection, missing data, active sensing and personalized monitoring, transfer learning, AutoML are all parts of our research agenda. Today, I'm going to talk only about a few of those that I feel need special attention. Also, another important pillar of the research that we do in our lab is making sure that these analytics are indeed interpretable and hence actionable for clinicians and patients. So work on machine learning interpretability, turning what I call black boxes into white boxes, an important part of the agenda. Another part is uncertainty quantification. So coming up with uncertainty estimates associated with these different predictions, such that we know when the clinicians can trust the model and when they cannot. Finally, we are developing a new branch of machine learning that we call quantitative epistemology. And the focus there is developing machine learning models to understand how medical providers understand the data, learn, and make decisions on behalf of their patients. So while the analytics part is more a decision support system, in quantitative epistemology, we go the other way around and we try to use machine learning to understand the humans and their decision making, to understand the black box in the clinician brain, and by doing so, empower them and understand what information would be most relevant to provide and what best support to provide. So in this way, we are moving to the next frontier in the human in the loop agenda. Till now, man and machine, if you like, were interacting really without machines helping us understand the data and understand the methods. Increasingly, we are moving to kind of the next generation of this partnership, where now machine learning can really become truly supportive of the decision-making process of the human. And again, the focus here is not at all replacement, it's quite the opposite, empowering with superpowers using machine learning the humans. And it is because of that that this last field interacts with all the others. Today, I'm not going to talk about it because that would require an entire talk and longer time. Instead, I'm going to focus more on the other parts of this agenda. And in particular, I'm going to talk about individualized treatment effect inference, interpretability, and time series data analysis. In order to motivate some of this work, I'm not going to motivate it with COVID. We have done quite a lot of work in the last year on COVID. And if you are interested to see our research in that area, you can take a look at our website. I'm going to motivate it instead with the cancer pathway because it's such a complex pathway. And I feel that a lot of pieces need to come together from your center, from our research, but also from many others in order to be able to really treat patients with cancer. And I do think machine learning can contribute to all the different parts of the cancer pathway. Today, I'm not going to talk about most of them. I'm just going to highlight a few. But if you are interested to see what is possible, you can see this Turing lecture, which I gave 2 years ago at the Alan Turing Institute, together with collaborators from Public Health England, from the National Cancer Registry. And you can see in that talk kind of both the data as well as what we have done a few years back to really support clinicians who are treating cancer patients. But as part of that partnership with Public Health England and NHS Digital, we discovered a few key challenges that we thought were easy and turned up as being very difficult. And they continue to be important milestones and challenges. So this is why I want to present them today, because I hope to join forces with you to conquer, hopefully, more of these problems. The first one and the first challenge is that of interpretability, explainability, and trustworthiness. So we cannot just come up with decision support systems like the one I described in the previous page. We need to really make sure that the models that we have are indeed interpretable, that different type of explanations are given to different categories of users. So for instance, for the clinician, we may want to have a certain type of interpretability, for patients, another type, and for the medical researcher or biological researchers, yet a different type of explainability, of interpretability. So this is why I define explainability as something more comprehensive, where different types of explanations are given to different stakeholders. And last but not least, also part of the agenda, but I'm not going to describe it today, is the whole idea of trustworthiness, and can we really come up with true coverage and true confidence intervals associated with these predictions. And just about the simplest part of the agenda, which continues to be challenging, making these black box models interpretable. And I have divided interpretability of black box models in 4 different categories. One is the more common used in machine learning literature, which is using patient features to explain what the machine learning model is looking at when issuing a prediction. So when I issue a prediction, for instance, for survival of a particular patient, we can highlight what features are important and what features are important over time for a black box model to issue these predictions. This is, let's say, type 1 interpretability. Another type of interpretability is to look at similar patients as found by the model. So is the model identifying these 2 patients which are seemingly similar to have the same prediction, or is the machine learning model issuing very different predictions for these seemingly similar patients? So it's through some similarities and differences that we explain the machine learning model's prediction and understanding of the data. The third type of interpretability is creating laws or hypotheses that could be either causal hypotheses or other types of laws, or possibly dynamical system equations that are learned by the black box model, which then become the laws or the hypothesis that was generated by the black box model, which can then be taken by a researcher to the lab and verified. The last type of interpretability is often mandated by medicine and in medicine, and that is the requirement to have a transparent risk equation associated with the predictions. So we no longer can say, I'm with prediction accuracy, this is the model. We also would like to have transparent risk equations. And if we can do so, there is no longer any advantage for regressions, because regressions are beautiful because they are transparent risk equations, linear equations. If we can show a nonlinear equation, but transparent one associated with the black box model, we are able then to pinpoint to anyone what machine learning and what nonlinear interactions may have been learned. And then, like in a regression model, we can interrogate it to get understanding. Let me start by talking briefly about type 1 interpretability and say that type 1 interpretability still remains an important workhorse of interpreting black box models, because we would like to take data and we would like to understand what features were important for this individual when the machine learning model, the black box model, issue a prediction. And a variety of methods exist. Our own lab developed one that's called InVase, which is an iClear 2018 paper. An advantage of InVase, as opposed to many other models such as Lime, Learning to Explain, Schaar, is that it's not only individualized, so I can issue different predictions for different individuals, excuse me, but also we are able to, I see that here, I also am able to identify the number of relevant features for each person. So it is this difference that enable us to identify that maybe for one patient is 3 features that are important, and for another individual there are maybe 2. And another advantage is that InVase is a very simple reinforcement learning method that can be trained very easily. And what would be one of my dreams would be once to align myself with somebody in your center to look at not only clinical data, so a lot of the work that I have done myself only focused on clinical data. I think it will be wonderful to train models that look at multimodal data, which includes imaging, genomics, and clinical data, and then use methodologies like InVase, which are very easy to train, to identify which features from the different modalities are indeed responsible for this particular prediction. This would be a lot more difficult to do with some of the other models, such as Lyman learning twins plane. In InVase, multimodal representations are easy to learn and easy to understand, to use for interpretability. So this is, if you like, an invitation for collaboration. Another type of ability that I again, transparent risk equations, because as we were working together with Public Health England, we realized that while the performance of our models was significantly better than the regression models that were currently used in practice, we had a disadvantage of not having transparent equations associated with these black box models. So how can we do that? So in recent work, we have built an entire agenda, and this is an agenda that was fulfilled in 2 subsequent papers that appeared in the last 2 years. We developed symbolic meta models that take black box models, whether it is a deep neural network or XGBoost or random forest, and turn them into a transparent risk equation. And these meta models are models of models, and symbolic meta models output a transparent risk equation describing the predictions of the black box model. And the idea is really that we can take these black box models and then project them into a space that's selected by the user. This could be polynomials, or it could be Bessel functions, or it could be whatever it's useful for that particular researcher. And then we are able in this way to identify white box models. For instance, we can have transparent risk equations that may be polynomials. And here is an example of how a particular transparent equation might look like. Why is this important? This is important because if we want to use these models in practice, we want to have understanding of these predictions. So a few years back, together with James Rudd, we have looked at UK Biobank, and we have made predictions for cardiovascular disease from UK Biobank. But one disadvantage of the work that we have done at that time was that we saw that our predictions are indeed better, but we couldn't explain beyond just feature importance why autoprognosis was better than the other models. Now, quite a few years later, we can. And I'm going to highlight this with the recently accepted Nature Machine Intelligence paper. So we have worked again very closely with NHS Digital to develop models for breast cancer prediction. And the workhorse currently in the UK for breast cancer prediction is a model called Predict, which was also developed in Cambridge. And it's basically a regression method. What we have done with autoprognosis, we have shown that the performance of autoprognosis is significantly better than Predict across all the populations in 2 different countries, both UK and the United States, and is significantly better for women that are difficult to predict, like old women and young women. But the disadvantage of autoprognosis was the same as when I was doing it with James, meaning that it was a black box model, and that was a disadvantage. So what we have done is we have developed these meta models due to this problem and are able to derive real transparent equations. I'm not going to put them on the screen. The analysis can be found in our paper. But what I want to tell you is that now, because we do have these transparent risk equations, we can throw away the autoprognosis model and instead use this approximation, which is this meta model, which is a white box model now, a nonlinear white box model. And what you can see is that it can issue predictions now, which are quite close to the original autoprognosis model and a lot better than Predict. So it is really my hope that now we can much more often rely on automated machine learning models and statistical models such as autoprognosis to really enhance the state of the art and then interpret them using meta models. But this is not completely done. A lot more needs to happen. And again, this is an invitation to everyone in your center to maybe consider collaborating on problems like this. We have these meta models, but we still need now to understand what features are important, variable importance. So we need to interrogate these black box models to understand variable interactions and finally come up with hypothesis generation to really understand physiology and biology. Also, if it is to use them for patients, to empower them to reduce their risk for particular outcome, what variables we should focus on to reduce this risk. So turning really these methods into actionable intelligence is still to come. Okay, I'd like, and again, if you want to get a little bit of a view of this, I have another Turing lecture given 1 year ago, just before the pandemic started, that describes these meta models in more details. And at the end of it, I have an entire discussion with clinicians about it. Let me now move to another area, which is that of modeling health and disease trajectories. And the reason I think medicine is especially interesting is that unlike in finance or smart cities or many other areas, when we want to develop models for time series analysis in medicine, we need to create models that are actionable, models that are able to integrate across a variety of data sets, models that have only limited supervision from clinicians. At times, different events in the past may matter, so history may matter. And interesting patients may have multiple morbidities and comorbidities. So there are different forces that are changing the predictions over time. And finally, not all patients are the same. They may have their own genetic characteristics, which may make them evolve differently. And last but not least, we need interpretability. One way in which we addressed this in the past was by building a new type of model, which married advantages of statistical models, such as hidden Markov models, which represent state-of-the-art, if you like, in interpretable machine learning and statistics for modeling trajectories of disease, but have the disadvantage that they cannot deal with very high dimensional and complex data, and also are stationary. They look only at the previous state. So we combine them with recurrent neural networks such that we have benefits of both worlds, thereby creating a general and versatile deep probabilistic model that can learn from complex data and come up with non-stationary representations. Unlike existing works in the deep learning that use attention either on the basis of the features or non-interpretable latent space of a neural network, in the attentive state space model, because we have as an output a probabilistic structure of state transitions like in HMMs, we have understanding as well. So this is a much better way, in my opinion, to do attention than the current ways in deep learning. And you can see that in here with this example. So we have state transition. Unlike in a hidden Markov model, we have non-stationary variable order models. And what you see here is that how these weights of past state are contributing to subsequent trajectories of disease. And in this way, and these weights are learned from data and can be individualized to the patient. And then we can say, this particular patient that has been diagnosed with cancer, let's say in stage 4, arrived in this stage 4 after a series of symptoms, and the transitions look like that. This will enable us to understand better trajectories of disease and do early diagnosis of cancer. We can also move into the future and say, we expect this patient to be moving in this way in the future, and maybe this moment is the best moment to intervene in a particular way to reduce these risks. Again, this is only part of the puzzle. Most of the work that we have done focused on clinical data, but it would be wonderful to combine imaging with clinical data as well as treatments to truly understand how the different measurements that have been done over time contribute to these trajectories of disease. So as somebody that is getting, I'm at high risk of breast cancer and I'm getting mammograms regularly and other imaging, I'd like to understand how past imaging information can be combined with other information from my electronic health record to really have an understanding of my trajectory of health and disease into the future. And this is, I would say, the next frontier, and we need to go beyond such attentive state-space models. Again, though, what's nice about medicine is that it obliged us to generalize a variety of methods that, of course, exist in the literature for a long time, whether it's continuous or discrete Markov models, semi-Markov models, variable order Markov models, but also neural networks such as multitask recurrent neural networks, deep Markov models, etc. Another point I'd like to highlight is what happens if these patients have morbidities and comorbidities. In that case, we would like to understand what type of events or others. And current ways to model morbidities are often one size fits all. So the entire population may have the same type of network of morbidities and interactions. And it's clear that we would like to personalize that. The other concern with existing models is that they are static rather than dynamic. And it is clear that it is not just the fact that somebody has a particular morbidity or symptom, but for how long they have had it untreated, that may lead to another event. So it is dynamic aspect that's not captured in practice. So again, by combining ideas from statistics with ideas from machine learning, we built a deep diffusion process, which is really able to model these temporal interactions between events over time. And we can, in this way, model these different events over time as a multidimensional point process with different types of intensities, and they are all modulated by the underlying, let's say, static information, such as genetic information of the patient. In this way, we can have personalized as well as dynamic morbidity networks. And I think that this is important because, again, we often say, well, it's interesting, patients with, again, referring back to my own work with James Rudd, we showed in the paper, for instance, that patients that have cardiovascular disease and have diabetes are at a different risk than the patients that don't have diabetes. But a piece of the puzzle still remains. Is diabetes for many years that matters? Is a recent diagnosis of diabetes that matters? How and when and for whom diabetes really matters in terms of their impact on their cardiovascular disease. So hopefully with these new tools in mind, we can start to have a much more refined analysis of patients with morbidities and comorbidities and understand what matters. Is the onset that matters, the duration of untreated morbidity that matters, etc. Finally, let me talk about personalized therapeutics, trying to understand what treatment we should be giving to a patient and when. I've talked already many times in Cambridge about treatment effects and estimating treatment effects from observational data. What I'd like to highlight here is kind of the next frontier, which is looking at treatment effects over time. So not only looking at shall we treat a patient, yes or no, but also when to treat, with what combination of treatments, and when to stop treatment. We know that clinical trials are often used for current decision making, but they are not adequate for this because treatment effects are often heterogeneous. And the randomized controlled trials focus on average treatment effects rather than identifying what treatments may be best for a subset of individuals. And while, of course, randomized controlled trials are and will remain the golden standard, they focus on small sample sizes. Patients that may have comorbidities or elderly may often not be recruited. They are often focused on a specific question and may not look at long-term outcomes and how the disease evolves over time, be unable to capture the complexity of care. Also, we cannot do randomized controlled trials for everything because they are going to be time-consuming, costly, and maybe at times unethical. So as a complement to clinical trials, we would like to learn from observational data, whether it's disease registries, UK Biobank, or electronic health records, which enable us to look at large sample sizes, representative patients, capture many aspects of healthcare. And if we can use machine learning, we can learn in a fast, inexpensive, and scalable way. Today, I'm going to focus on more recent work rather than work that I have highlighted in the past. I'm going to look at longitudinal trajectories, which I think are especially interesting. And there are many observations that we can get from the electronic health records of patients. We have mainly looked again at clinical data, but imaging data that your center is looking at is a very important piece of the puzzle. And I really hope, again, this is an invitation to join forces to do something together on this agenda. So we have different types of time-dependent features, treatments over time, as well as static patient variables such as genetic information. This is the patient history. Also in electronic health records, we have the outcome of the patient. So what happens to this particular patient and what happens to them over time. The challenge is we only have the factuals. We do not have the counterfactuals. So we do not know what would have happened to these patients if they were treated at a different moment in time and potentially treated differently. So counterfactuals are not available. So what we are trying to solve is trying to understand for an individual when to treat, how to treat, and when to stop treatment. This problem has been formalized for many years, initially in the static setting by Rubin and Neyman, and more recently by Robbins and Hernan for the longitudinal setting. And this fits under, so this is not a prediction problem because we do not observe counterfactuals and we have biased data. It's a causal effect inference problem. And this causal effect inference problem over time requires us to estimate for the possible treatments in the future potential outcomes under planned sequence of future interventions. To be able to address this problem, we usually, but not always, make two assumptions that are quite strong: sequential overlap and sequential strong ignorability, or in other words, we don't have hidden confounders. Under these two assumptions, we are trying to solve this problem. And unlike the static setting, which I described before in many talks that I gave in Cambridge, there is another challenge in the longitudinal setting: the fact that we deal with time-dependent confounders, and they are going to bias the treatment assignment. So what are these time-dependent confounders? They are covariates that are affected by past treatments, which then influence future treatments and outcomes. A good example of that is side effects, which are going to be influenced and affected by the past treatment and will in turn influence future treatments. So the challenge in the time series setting is that we don't only need to deal with bias, but also bias from these time-dependent confounders. One way in which the literature has addressed that in the past, I would say the workhorse of this has been marginal structural models as introduced by Robin, Hernan, and Brumbach. And indeed, a few years back, we have built on marginal structural models by introducing recurrent neural networks, deep learning methods to learn from more complex data. Because marginal structural models are quite complicated. They are not very good at integrated complex data sets. However, these models, both the original marginal structural model and our version of it based on recurrent neural networks, are based on inverse probability of treatment weighting to deal with this confounding bias. And these methods, when taken to many data sets, we observe that they are numerically unstable and have high variance. So recently, we developed another way to deal with this problem, with the problem of time-dependent confounders, by introducing counterfactual recurrent neural networks, which learn balanced representations for to build this treatment invariance. So how do these methods work? The way in which they work is by using first a sequence-to-sequence architecture. Sequence-to-sequence architectures have been very powerful in machine learning for translation, where I'm translating from one language to another. You can view this problem of treatment effects over time similarly. You take data from prior to treatment, and then the treatment, it acts almost like a translation to a new language, the patient after the treatment. So you can use them to project into the future for different types of translations on the basis of different types of treatments at different moments in time. However, unlike the conventional natural language processing, again, medicine brings new frontiers to machine learning, because in language, we don't deal with bias. what we do in these data sets, medical data sets, we need to deal with this time-dependent confounding bias. So in order to create representations that are treatment invariant and they deal with this bias, we use domain adversarial training. So these counterfactual recurrent neural networks are a combination of sequence-to-sequence architecture, but which are trained in a quite innovative way over time with domain adversarial training. Again, I think a lot more can be done in this agenda, especially by combining a variety of modalities. If you want to take a look at these various works I highlighted here, just today, actually, the iClear conference is taking place. And just today, actually, we are presenting a paper called Clairvoyance, which is, I think, a new frontier for machine learning in medicine, because it's an open source, unified end-to-end pipeline for clinical decision support, which contains all these different modules. So if you want to play with the counterfactual recurrent neural network, with Invase, with the time series models that I described, you can take a look at Clairvoyance, download it and play with it, and introduce your own models, your own data, and augment it. We really hope it becomes a way to build on top of each other's work easily. And this brings me to the conclusion. I often say it's really machine learning, but also statistics, applied mathematics have a lot to offer, I think, to really provide this revolution in healthcare, both to empower clinicians, to enable new discoveries, to integrate a variety of data, imaging, as well as omics, as well as together with pharma, enable new therapeutics. And as you know, together with a few members of the Cambridge community, Sanger, as well as AstraZeneca and GSK, we just recently started this Cambridge Center for AI in Medicine that I think it's very complementary, different, but nicely complementary to your center. And I really hope that a lot of collaborations are going to come in the years to come in Cambridge with these two centers. Thank you so much.
Thank you, Mihaela. That was a very inspiring and very impressive talk that I'm sure touches upon the research of many of the attendees. I'm very curious to hear any questions directly related to your talk, and perhaps one or two opportunities for or pitches for collaboration, because the door is wide open. That's clear. Any questions for Mihaela? You can type them up in the chat. And maybe as a start, one of the most interesting things I took away from your presentation is kind of the meta models that you talked about, and there will always be, as I understand it, a performance penalty from projecting your learned optimal model onto kind of this more interpretable this interpretable version. I have a few questions around that, but first off, what do you think is an acceptable penalty to pay there, and do you think that this differs across domains in medicine?
So thank you for this question. So I am not the right person to say that. I think it's the users of these models that will need to kind of make the decision. But what I think it's interesting is the fact that now we can get medical researchers like James Rudd and others to look at these models and not only just use them for prediction, but also try to see if there is something interesting that's unraveled by the machine learning model. So in our collaboration on breast cancer, it was very interesting to identify that these machine learning models learn very interesting nonlinear interactions. Some that were known in the literature, some that were not. So I would say this penalty is, let's say, this drop in performance. If you want to have a very parsimonious and very compact model, You may decide on projections that are more compact and sacrifice some of the performance that may provide part of the explanation and part of the prediction power. But maybe for some subclasses of patients, again, maybe patients with diabetes, allowing for some additional terms to be presented, which will improve both the performance but the understanding, would be an interesting way maybe to go about it. So again, let me use this as a platform and as an invitation to medical researchers in general to see, can we take together now some of these meta models to understand how parsimonious, how compact these representations can become? Can they become very compact for the general population? Maybe for some subclasses of patients, we need more parameters, we need more terms, and we need more nonlinear interactions. It's now finally an opportunity to interrogate that. And it's also, if you like, I'd like to issue a challenge to some of the lovers of regression models, because often people say, oh, I use regressions because they're very interpretable. But then I think relatively few people start to do research using these models and say, is indeed really, are these variables that the regression model has learned indeed making sense biologically?
Yeah. And in that sense, it might also help in target discovery, perhaps even.
Exactly.
Some great questions coming up.
It's an invitation, I'd say.
Yeah. Some great questions coming up. I'm gonna read out James Rudd's question, who's really wondering for the next step in your view of explainable machine learning. Can you comment on that?
So thank you, James. So first, as some of you may know, we have started and slowly are progressing. We didn't get yet to cardiovascular disease, but hopefully we'll get there soon. We started an entire set of engagement sessions with clinicians that we call Revolutionizing Healthcare, partially to develop methods that are truly useful for clinicians. But what's next in interpretable machine learning? So we are doing a lot of work on time series interpretability. We are also doing a lot of work on trying to learn similar patients beyond what we have done so far. Because based on my discussions with clinicians in this Revolutionizing Healthcare, what they are saying is interpretability may be not so important for me, the clinician, trustworthiness may be even more, but for my patient, it is very important. My patient wants to know why certain predictions have been made, and being able to identify similar and different patients and possibly over time, it's an important frontier. So this is what we are working on as we speak. Another thing on interpretability, James, that we are working on is trying to understand human that I highlighted, but I didn't talk about, which I call quantitative epistemology, trying to use machine learning to understand why a clinician. We always like, if we get sick, to get to the best clinician. And we hope that this best clinician has superpowers to look at our symptoms and our trajectories and issue a particular diagnosis or recommendation for us. We are trying with these machine learning methods to X-ray the decision-making process of the clinicians. And we hope that in this way, we can create understandable mental maps of the decision process of the clinician. And if we understand that, then maybe not only we can identify variation in practice and good variation in practice, but also we can build more interpretable machine learning models that can prompt the clinician to say, we believe you are integrating information in this way, but didn't you maybe forgot that this patient has diabetes and hence you need to integrate this other information as well.
Perfect.
So
thanks, Mihaela. I look forward to the next collaboration.
Thank you, Mihaela. I think you've inspired all of us. We'll certainly look up your talks on your website. Yeah, for everyone. Sorry, Sophia, we didn't get to your question. We do have to move to the next speaker, but it's clear that the door is open, and I really hope there will be some fruitful collaboration.
Yeah, and for Sophia, I look forward to talk to you more. And I just want to say we have an entire set of papers dedicated to machine learning for randomized controlled trials, going beyond our own collaboration. So please just take a look and let's get in touch. Thank you.
Perfect.
Thank you for inviting me.
Thank you, Mihaela. And then